Imagine you have a really complex document, maybe a pharmaceutical trial report or a super detailed financial prospectus, maybe even hundreds of pages of old, scanned legal papers. And your job is to get everything out. The tables, those tricky formulas, captions, all the text blocks, and this is crucial, you need it all in the correct human reading order. For, well, decades, this has just been a huge data bottleneck, a really frustrating, often expensive challenge for automation. So today we're doing a deep dive into a new solution that honestly looks like it could cut right through that complexity. It's a vision language model called dots.ocr, and it's delivering state-of-the-art performance for document parsing by, unifying what used to be a pretty messy multi-step process. I'm Jack Malik, and just so you know, I am an AI-generated voice.
And I'm Sophia Lane, also an AI-generated voice. Hi, everyone. We're excited to explore how this, well, quite compact VLM manages to get such impressive results. And just for context, this analysis is a part of the content for the podcast Artificial Intelligence, Papers and Concepts, which is curated by Dr. Satya Malik.
So the core mission here isn't just about, reading text. It's really about understanding the page layout and the content at the same time. When we talk about the old document parsing pipelines, it often feels like you're building some kind of Rube Goldberg machine, right?
That's actually a great way to put it, yeah. Conventionally, you needed one model just to find the boxes for tables and text. That's layout detection. Then another specialized model for the actual character recognition, the OCR part. And then often you'd have another system trying to piece together the right reading order afterwards. It gets complicated fast. The big innovation with dots.ocr is that it's a single, quite powerful, multilingual vision language model that just pulls all those functions together.
Which really changes the game for developers, I imagine. Instead of trying to chain together maybe 5 different libraries and just hoping they work well, you have this one single interface. But why does putting it all together lead to better scores? Not just, simpler code. You might think specialized models would be better at their one job.
That's the really interesting part. By handling layout and content recognition basically simultaneously, the model avoids those cascading errors that you often see in multi-stage pipelines. Like, if the layout detection makes a mistake early on in the old system, that immediately messes up the OCR and the reading order down the line. Dots.ocr makes a more holistic judgment about the document in one go. This really boosts the reliability of that final output, especially for something critical like keeping the reading order correct.
Okay, let's unpack this a bit more. Let's talk about the engine powering it. You hear SOTA results, you probably expect some massive foundational LLM, right? But this is built on a pretty compact 1.7 billion parameter LLM foundation. The whole model size is just 3 billion parameters overall. That seems, well, surprisingly small for achieving top results. Relatively small foundation getting big results. Is there a catch? A trade-off somewhere?
Well, that's what's so interesting. The trade-off seems minimal. That small size, specifically the 3 billion parameters using the Safe Tensor's BF16 format, it translates directly into really fast inference speeds. So you get efficiency, but without really sacrificing the accuracy much. It means it can deliver competitive or even faster throughput compared to many big models based on foundations maybe 10, 20 times larger.
Before we get into those performance numbers, just a quick note. This deep dive was sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai. Okay, so we get the unified architecture, we get the efficiency boost. Let's talk hard numbers now, because that's the real proof, isn't it? The model is hitting state-of-the-art status on major benchmarks, particularly OmniDocBench. This isn't just a minor improvement.
Exactly. And if you're someone looking to automate document processing, the key metric to watch is edit distance. It basically measures how many single character changes like inserts, deletes, or swaps are needed to fix the model's output so it perfectly matches the original document. You want that score as close to 0 as possible. 0 means perfect.
Right. And on that crucial overall parsing score, dots.ocr's numbers are, well, pretty stunning. On OmniDocBench, it gets 0.125 for English, 0.160 for Chinese. That's demonstrably better than massive general VLMs like Gemini 2.5 Pro and GPT-4o on that specific measure. In practical terms, a score like that means the amount of manual checking needed afterwards could potentially drop significantly compared to older solutions.
And we can even drill down into the text recognition performance across different types of documents. Think about the variety out there. Books, complex financial reports, dense academic papers. Dots.ocr gets the best overall result here, with the lowest average edit distance of just 0.055. And it's not just a fluke average, it scores lowest in almost every single category. For academic papers, which are often full of tricky formatting, the score is an amazing 0.029. That kind of precision is, well, potentially transformative.
Okay, wait, here's a really interesting point, especially thinking about that unified VLM idea, defying conventional wisdom, layout detection. We usually assume, right, that a traditional specialized detection model, like a YOLO-based one, will always be better at just finding the boxes, spatial awareness. But dots.ocr's F1 score for detection is 0.845 when it's just doing detection-only tasks.
And that F1 score uses a pretty tough metric, F1 at IOU 0.50, 0.05, 0.95. It basically measures how well the predicted boxes match the real boxes across a range of overlap thresholds. Getting 0.845 there decisively beats traditional dedicated detection models. They mentioned DocLayout YOLO DocStruct-bench scoring 0.733. So it really proves that this unified VLM structure isn't just simpler to use. It might actually be achieving better spatial understanding by linking the content context directly to the bounding box prediction. Pretty neat.
And what about the really tough stuff, like tables and formulas? Those are always the nightmare for document parsing. How does this relatively compact model handle those details?
It holds its own surprisingly well. Yeah, while it's smaller, dots.ocr delivers formula recognition results that are comparable to much, much larger models like Dubao 1.5 and Gemini 2.5 Pro. And again, the focus seems to be on making sure the extracted data is actually usable. They confirm state-of-the-art performance in the read-order-edit distance on OmniDocBench too. Because, let's face it, if the model reads a column of numbers perfectly but spits them out in the wrong order, that data is useless, right? So getting SOTA in reading order means the practical utility is just extremely high.
That strong performance carries over nicely to its global reach, too. The multilingual support is obviously critical for any modern application these days. And the developers didn't just test, like, English and maybe Spanish. Their own internal benchmark, dots.ocr-bench, used 1493 PDF images covering an incredible 100 languages.
Yeah, that's huge, especially for companies dealing with low resource languages where good tools are often lacking. On that specific multilingual benchmark, dots.ocr got an overall edit distance of 0.177. That significantly beat competitors like Gemini 2.5 Pro, which scored 0.251. So it really suggests robust, real-world parsing ability for documents pretty much anywhere in the world, basically right out of the box.
Okay, so the architecture is compact, the performance is SOTA, language support is broad. How easy is this thing to actually use? Let's talk about the aha moment for developers using it.
Right, the simplicity is kind of the final key piece. Because it's this unified VLM, switching between different tasks is super straightforward. Let's say you only want the layout detection part, maybe to crop an image, or perhaps you want the full text and layout parsing. You just change the input prompt you give the model. You're not swapping out different models or libraries, you're just tweaking the instructions.
And the output format is crucial for integration. You mentioned it delivers everything in a single JSON object. That's exactly what developers want. What's inside that JSON? How's it structured to be immediately useful?
It's very well structured. For every single element it identifies on the page, like a caption, a formula, a table, just regular text, or a title, the JSON gives you its bounding box coordinates, boobox, its category, and the actual text content. But the real value add is in the formatting rules that get applied through the prompt. Formulas come out formatted as LaTeX.
Oh, wow.
Yeah, so you could potentially drop that output directly into a scientific computing tool or document without manual transcription. Tables are formatted as HTML, making them instantly easy to parse or display in a web context.
And everything else just gets clean Markdown formatting. So the data isn't just pulled out, it's immediately structured in a way you can actually use for computation or display.
Precisely. And the model has constraints built in. The output text has to be the original text. No accidental summarizing or translations sneak in. And crucially, it must be sorted according to human reading order. So you get data that's clean, structured, flows correctly, and is basically ready for whatever downstream task you have planned.
Of course, no tech is perfect, especially when tackling something this complex. As powerful as dots.ocr sounds, we should definitely talk about the current limitations. What are the roadblocks or the big gotchas people should be aware of right now?
Yeah, absolutely. The developers are quite upfront about the current limitations. While performance is strong overall, it's not yet perfect for really, really high complexity tables and formulas, especially if there's a lot of visual ambiguity on the page.
And a pretty major constraint right now involves visual content that isn't text, right? Like images embedded in the document.
Exactly. Currently, the content inside pictures within documents, so things like graphs, embedded charts, diagrams, maybe tiny text labels within an illustration, that content isn't parsed. The model will identify the bounding box for the picture category, but the text content field for that element will be empty. That's obviously a significant gap, especially for understanding scientific papers or technical reports fully.
That makes sense.
There's also the throughput question. While the model itself is compact and fast for its size, it's not yet fully optimized for, say, massive enterprise-scale, high-throughput processing of millions of PDFs daily, so that could still be a performance bottleneck if you're operating at that kind of extreme scale.
We should also probably mention the specific failure modes they documented because, well, some of them sound a bit weird.
They are a bit strange, but important to know about, yeah. The documentation mentions that parsing can fail if the character-to-pixel ratio is way too high, like if the text is incredibly tiny compared to the image resolution. That can lead to noisy, unreliable predictions. But maybe the most bizarre failure mode they noted is when the model encounters a long, continuous string of special characters, like a line full of ellipses or underscores. Apparently, it can sometimes just get stuck in an infinite loop, just repeating that prediction over and over until it fills the output buffer.
Oof, yeah, that sounds like a developer's nightmare scenario right there, finding and fixing that kind of bug. But clearly, the team behind it is focused on improving things. So what does all this suggest for the future trajectory of document parsing technology?
Well, the long-term vision seems pretty clear. They're aiming for the continued development of a more general-purpose perception model based on VLMs. The goal is to integrate general object detection, image captioning capabilities, and OCR into an even more refined and unified framework.
So logically, the next big hurdle, the key future priority, has to be tackling that visual content gap we talked about. Being able to parse the graphs, the charts, the text embedded inside the pictures within documents, that feels like the next major leap forward. It would turn documents from just static containers of text into fully understandable semantic data sources.
Absolutely. So just to kind of recap the big impact here, dots.ocr is delivering state-of-the-art performance, especially in text recognition and that all-important reading order. And it's doing this within a remarkably small, unified 3 billion parameter VLM that works across 100 languages, all driven by a simple prompt interface. It really feels like it's fundamentally changing how we can approach document intelligence, getting high precision at impressive speed. And maybe here's a final thought for you to chew on. Since this model is already hitting SOTA in reading order and text recognition using this prompt-driven, unified approach, what truly revolutionary possibilities open up when document VLMs can finally seamlessly parse and understand the visual content inside the pictures just as well as they handle the surrounding text? That feels like the really exciting frontier to watch in the next year or so.
That is a truly thought-provoking question to leave everyone with. Thank you so much for tuning into this deep dive today. Please make sure you subscribe to our deep dive for more cutting-edge analysis and knowledge like this.